guys. Moving on to chapter 2 in our Electrotechnology 2 book. I hope you guys got my WhatsApp there. Sorry about that. And yeah, so we're finally starting on chapter 2, and it's just we're looking at DC circuit analysis and theorems, right? So we still continue with circuit analysis. The chapter after this will be energy, small chapter which will probably take a week or so. In fact, it will take a week to complete. A very nice light chapter. But for this one, this is where the crux of the work is. So by the end of the term, we will have covered 5 chapters. This is the plan. So we're doing good here, right? Okay, let's go on. So why is it important to understand this circuit theory? Okay, so in the previous chapters, it is seen that a single equivalent resistance can be found when 2 or more resistors are connected in either series, parallel, or a combination of both. And these circuits obey Ohm's law. So essentially, that is just kind of encapsulating exactly what we've done in the previous lectures. Just to we're using Ohm law, it's finding resistance, voltage, currents, right? But now, sometimes more complex circuits, we cannot use Ohm's law alone to find voltage and currents circuit within the current. For these types, we use certain rules to obtain certain equations, and then we use Kirchhoff's law. Kirchhoff's law is a very powerful law, and this is what we're starting with today. And then there's also other theorems, superposition, Thevenin, Norton. That's what we'll be covering here. But also, there's also a number of other approaches. There's Kirchhoff's law, superposition, Thevenin, Norton, which is covered in the book. There's maximum power theorem, mesh current, and nodal analysis. The last two is my favorite. I think for us, we'll be only covering the first four half there. And there's a good book by Robert L. Boylston. It's essentially focusing on strictly circuits. Now, normally in electrical engineering, how things are conducted is that they have a subject called electrical engineering, which solely focuses on circuit analysis. Now, with us, with electrotechnology, we take a bit of power systems, 3-phase and motors. We take a bit of electrical machines and we mix it up into one subject. So our subject is comprised of both electrical engineering and electrical machines. So that's how we talk. But that book is solely based on circuit analysis, and it's a very good book. Of course, that's just for reinforcement. There's a lot of advanced techniques there. It's like the creme de la creme of circuits. But of course, I don't want to talk too much about that. We are going on with ours. Just give me a second to have a quick call to answer. Okay, I'm back. So, what is Kirchhoff? So, Kirchhoff laws can also be applied both to DC and AC circuits. And it has two branch of laws, right? So, the one is the current law. So, what is the current law? It's basically at any junction, right? So, any junction, like we have branch two branches, the total current flowing towards a junction is equal to the total current flowing away from the junction. Again, this is analogous to pipes, water in pipes. So if you look at the figure 13.1 over there, you can see I1 is going in and I2 is going in to that point. Then we get I3 going out, I4 and I5. So what's going in must equal what's going out. That is essentially what's happening with it's a fairly straightforward law to think about. So just think of water again in the pipe. Second is the voltage law. So in the voltage law, so in any closed loop in a network, the algebraic sum of the voltage drops, products of current and resistance. So of course, there can be resistors as well. Taken around a loop is equal to the resultant EMF. So that seems a bit tricky, but the idea is that if we look at the figure there at the bottom, we have to follow the flow. So if you look at E1 is going, E1 is flowing from positive to negative. So it goes around, but then you have another battery there with E2, which opposes that flow. So then we say negative E2, and of course that's all going to equal all the individual resistance over there. So we'll get into that. You've touched on Kirchhoff a bit. They're saying note that if a current flows away from a positive terminal source, that source is considered by convention positive. Thus, moving anti-clockwise around the loop, E1 is positive and E2 is negative. So if you take one source, that's the flow. Then, of course, the other ones going against will be negative. The EMF source. Now, the EMF source is ideal voltage source with no resistance. And it's like the ideal battery. It's just used for ideal analysis, circuit analysis. Okay, so let's quickly touch on an example over here. There we go. So if you remember this, here we got a voltage, a battery there with two cells, and we've got one. And what we're required to do is, and of course, you can even touch on your electrodes, one book if you still have it. And we're going to have to apply Kirchhoff's to this particular circuit, right? So can you see for normal circuit, it won't be that easy. We use our normal laws because now we have two voltage sources. So now we have to kind of play around with what we're doing. So let me just quickly, once again, go to my blackboard with this for you. And then we can actually have a look. So I'll just give a quick recap of Kirchhoff's law. Of course, the sheet starts off like this, but you can imagine you're going to be having a certain amount of branches four. Okay, all right. Let me share my board with you again, and then fantastic. Okay, so you guys see my board, right? Okay, so if you recall Kirchhoff's law, the idea is about taking loops. Remember, taking loops. So what we can do here is the first approach is normally we take one loop going with the EMF, you can say loop 1, and we take another loop going this way, right? But what's important also is to identify the current flow. So here, E1 puts out a current, I1, E2 puts out a current. You guys are you all with me? That's I2, and of course they rejoin over here, and this becomes I3 at this branch. So they actually, we add, so we know that I1 plus I2 equals I3, right? So I'm assuming you guys are familiar with this. So how we take Kirchhoff's, we're going to look at our voltage laws now. That is the first thing. And we look at voltage laws here, right? This is what we're going to start. We say the first voltage, which is the EMF, goes around, and then we kind of collect resistors as we move along here. So we know that E1 is 4. And as we go here, I1 is flowing through here, but in fact it's I1, in fact it's I3 here going through this is, so that's I3 times 4, plus as we go around here, this will now be I1 solely in this branch over here. Let me first make sure. 4 equals 2I1. Yeah, so I1 is essentially, because when this flows here, and I should have mentioned this, that becomes again I1, and that's again I2. I3 again splits back that way. So then we have 4 times I3, right? And then we have I1 times 2. And of course, we can split this up, and I'll put this in this form. And this is going to be now I3 is I1 plus I2 times 4. And we sum all of them up. This is going to be 6 I1 plus 4 I2. So I hope you guys all agree. So you can see that's the EMF, and of course there's no other EMF within this loop over here, so we don't subtract anything. And then we just kind of go around. We can start in this branch, it's I3 over there, and then we have I1 over there. So is everyone happy with my first equation here? You guys concur with this first loop? Okay, so for recap here. Next, look at the next loop, and it's loop 2. And now remember, we're going from positive to negative, so we're only looking at this portion over here. So we know that the second part is going to be 2, and again, it's still I3 in that branch, so it's I3 times 4, and it goes, and we're going around, and it comes up here, and that's I2 now again, so it's plus I2 times 1. And if we just write this again in order, with I1 being there, it's going to be 2 equals I1 4 plus I2 5. And then we've got 2 equations, right? Is everyone happy with this one? Is everyone happy with this? Hello? Where does the 5 come from? Remember, we're adding here. I didn't do this in steps, so I had a feeling people are going to miss this. So 2 equals, remember, I3 is I1 plus I2 times 4 plus I2 and 1. You see there? So of course, if you add that guy and that guy, you get 5. You see it now? Now, what is the next step? Who can tell me? Someone speak to me. It's been awfully quiet here.
We need to solve the equation, sir.
Yes.
Yes,
and how do we solve it?
We find first, we choose, if we find the E1,
Yeah.
after we find the E1, we substitute on the second equation and find the E2. Yeah, it's
Okay.
gonna work with.
I'm with you. So now you guys are big boys, and this is why you done matrices, and I'm going to show you what you need to do now, right? So you gotta make a matrix, and this is why we use beautiful Casio calculators. And what we do now, we have a 2 by 2 matrix, if you can see it, right? And this is going to be equal. So here we have I1 and I2. And we're looking for I1 and we're looking for I2. So I1 in the first equation is 6. I2 is 4. That's the first line. And that is equal to 4, right? 4 positive. The next thing we do now, we look at this line. So I1 is 4. This guy is 5, and our EMF is 2. So once we have a 2 by 2 matrix, and a question like this, I give marks probably here. So it's probably 1, 2 marks, 1, 2 marks, and 1, 2 marks for writing out your method. You can solve it by substitution. I am an engineer. I'm an educated engineer, so I use matrices. And I'm going to show you now on your calculator how you're going to do this, right? So can you please just remember this matrix? Can you just write it down quickly? I'll give you a minute, like quick. I can prepare my calculator and show you how to solve the matrix. Okay, do you guys have it? Can I go? Okay. Where am I? Why am I? Okay, so I'll share my calculator now. So just give me a second. There's no negatives in my matrix, right? So just to make sure that it's all positives. Okay. So let me just share this. Open my calculator up. There we go. Let me know when you see it. So first step. This only works with the Casio F991ZA plus. You go to mode. You go to number 5, equation, and we have a list of 4 options here, right? So the first option is for 2 unknowns, a 2 by 2 matrix. The third is a 3 by 3 matrix. Third one is to solve a quadratic equation. The fourth one is to solve a cubic equation. So I'm going to choose 1. So there is my matrix. So remember, my I1 was 6, I2 4 for the first equation, and that's 4. That's the EMF here, right? And then 4 I1, and the other one was 5 I2, 2 for the EMF. And once you have that, all you got to do now, Ivano, is press equal, and there you got your I1, and I1 is 0.8574. So I'll write it down in my end here. So long. You guys like that? 85714 amps, and we click again, equal. You get I2, and it's minus 0.2857. Is everyone happy with that? What do you think of that? Instead of wasting time by substitution. You guys okay? Quick. Yes. If this is quick, the sums can be long. You still going to have to apply. Instead of doing the outdated substitution. Okay. So I'll go back to my blackboard, or my whiteboard, whatever we call it. And then I've written my I1 and I2. And of course, we know that I3 is simply algebraic sum. So we add them up and we should get 0.571 amps. And of course, we probably get 2 marks here, 2 marks there, 2 marks there. Okay. Now to end off here, I'm going to show you how Kirchhoff works, right? Now, instead of taking those 2 loops, you have an option of taking another loop, right? And if you look at, and what I mean by this, so this is why I like this section, because it's a lot of creativity here. You don't succumb to one approach all the time. So what I'm saying is, we can take another loop here, and this loop is going to be from here right around. So of course we still need 2 loops. So I'll keep loop 1. So my first loop was 4 equals what's it? 6I1 plus 4I2. And now for loop 3, so loop 3 will be the whole thing around. I'm find another equation. So instead of me taking this inside loop 2, so here I'm going to say now I subtract my EMF. So it's 4 minus 2. And the reason why, because that is going against that one. 4 minus 2, I mentioned this to you. E1 minus E2. And of course, we collect our things around here. And that's going to be that is still I2, right? So we're going to say, but I2 is going in the negative direction because it's being produced this way. So minus I2 and 1, of course it's resistance, and I1 is going the same direction as the loop, so it's going to be plus I1 times 2, right? And of course this is 4 E1, that's minus 2. I'm just going to put this in the positive form so it looks better, and of course it stays 1. Then we have 2 equals 2 I1 minus I2, right? And once we have that, we've got another equation. We can call it equation 2 now for in this case. And then we can make the same matrix, and it's going to be 6 and 4 and 2 and negative 1. And I'd like you to practice with the calculator. And this is going to be, so the voltage for this one was 4. This guy was 2. And of course, this, oh, sorry, it's not correct here. This must be I1 times I2. And that's going to be equal to your voltage, and this was going to be 2. And this voltage is 4 at the first equation, and the second one is 1. Sorry, 2. My bad. Okay, so if you do this matrix, what is I1 and I2? Just check in the calculator. Can you please check for me? I'll leave this up to you. What you guys get? Yeah, exactly. Thank you, Mr. Ramasuri. Can everyone please check? I think Puleng, she likes Electrotech. So, Mr. Matoso, Jason is awfully quiet. What do you guys get? Okay, and of course, you click again, I2 put exactly the same value. Yeah, I'm sorry about that. Yeah. So I recommend getting in Casio. So okay, guys. I hope you enjoyed today's lectures. Thank you. So can you see the power of the calculator? Um, and I'll see you next week to carry on with DC circuit theorems. We'll probably conclude there. And yes, yeah, thank you very much. I'll see you at 1 again.